This study investigates the dynamic behavior of polyelectrolyte chains in aqueous solution, focusing particularly on how interchain hydrodynamic interactions and internal friction influence their motion. Understanding these dynamics is essential because polyelectrolytes are widely used in biological and industrial applications, from drug delivery to water treatment, where their solution behavior affects performance. The key question addressed is how macroscopic properties like collective diffusion correlate with segmental chain dynamics, especially under varying ionic conditions. To explore this, the authors use a combined experimental and theoretical approach. They measure collective diffusion using dynamic light scattering and self-diffusion via pulsed field gradient nuclear magnetic resonance. On a more microscopic level, they use neutron spin echo spectroscopy to probe chain segment motion, interpreted through the ZIM model, including internal friction. This work further introduces a hydrodynamic interaction screening radius to reconcile the transition from segmental to collective behavior. The goal is to establish a comprehensive description of charged polyelectrolyte dynamics from dilute to semi-dilute solutions, accounting for polymer charge, ion concentration, and internal friction effects. Such a multi-scale understanding is crucial for predicting and controlling polymer solution properties in various environments. Figure 1 presents measurements of the collective diffusion coefficient, DC, via DLS, and the self-diffusion coefficient, DS, by PFG NMR for polystyrene sulfonate of molecular weight 39 kg per mole, PSS 39K. The data are shown for different polymer types, acidic H or sodium salt, Na, and varying added NaCl salt concentration, CS. The solid symbols represent DC, capturing how groups of chains diffuse collectively, while open symbols show DS, reflecting individual chain mobility. The authors highlight that at high salt concentrations, extrapolating DC toward dilute conditions aligns well with DS, indicating consistent chain behavior. In contrast, at low salt concentrations, DC is up to 10 times larger than DS, showing that collective diffusion dominates. The left inset plots DS against the total ion concentration CI, which includes contributions from added salt, counterions, and water dissociation, factoring in an effective 8% dissociation due to ion condensation on the chains. This plot reveals that self-diffusion increases with increasing ion concentration approximately to the 0.2 power. The right inset relates the monomer overlap concentration NCP star, calculated from DS, indicating when polymer chains start to physically overlap and semi-dilute behavior emerges. For lower ion concentrations below 100 mm, several polymer concentrations lie above this overlap threshold, suggesting semi-dilute conditions, while higher salt concentrations correspond to dilute solutions. The authors interpret these trends as showing that electrostatic repulsion extends chain dimensions at low ion concentrations, reducing self-diffusion, while added salt screens these interactions and reduces hydrodynamic radius. Overall, the data indicate complex dependencies of diffusion on salt concentration and polymer charge state, setting the stage for understanding interchain and internal friction effects. Figure 2 shows small-angle X-ray scattering, SAXS data for PSS 39K after background correction and scaling by concentration. The observed scattering intensity IQ reflects the product of individual polymer form factors and their structure factor SQ, which describes interchain correlations. The data span various polymer concentrations and salt conditions, with color coding indicating increasing polymer concentration. The key observation is that at low Q values, the intensity decreases more strongly with increasing polymer concentration due to a pronounced structure factor effect, indicating stronger interchain interactions. The structure factor SQ is modeled using a 2Yukawa 2Y form, which captures a screened electrostatic repulsion occurring on a nanometer scale, together with a short-range attraction below 0.3 nanometers. The authors attribute this attractive component to hydrophobic effects from the polymer backbone, the influence of condensed Na+ counterions, or excluded volume effects. Notably, increasing salt concentration reduces electrostatic repulsion by screening, resulting in a weaker structure factor, as reflected in the SAXS profiles and the fits shown as black lines. For the highest salt concentration studied, the repulsive contribution in the 2Yukawa model was fixed to negligible, indicating near absence of electrostatic repulsive interactions. The broken lines in the figure indicate the Q-squared decay region of the scattering, consistent with polymer chain form factor behavior. These SACS results provide crucial structural context, showing how salt concentration and polymer concentration modulate interchain interactions and polymer conformation in solution. Important factors linked to the diffusion phenomena discussed. Figure 3 shows neutron spin echo (NSE) measurements of the normalized intermediate scattering function IQT times IQ0 for PSS 39K at 500 mm salt concentration and 30 mg per milliliter polymer concentration, collected at the ILL in Grenoble. This function captures the time-dependent segmental motion of polymer chains over nanosecond to 100 nanosecond timescales and length scales related to wave vector 2, which is detailed further in Figure 4. Additionally, the figure includes a synthetic data point at low Q corresponding to the collective diffusion coefficient DC, measured independently by DLS. The authors fit these data using the ZIM model with internal friction, corrected by the ratio of hydrodynamic to structure factor, HQ times SQ, to account for interchain interactions. The fits, represented as solid lines, generally show excellent agreement with the experimental data, indicating that the model successfully captures chain dynamics incorporating hydrodynamic interactions and internal friction effects. The data span a range of timescales that allow observing a crossover from collective diffusion at low Q to segmental chain relaxation at higher Q. The authors emphasize that their model assumes local chain dynamics decouple from interchain hydrodynamic interactions. Moreover, analyzing effective diffusion coefficients derived from these measurements reveals a ZIM-like behavior over certain Q ranges, but with deviations at higher Q attributed to internal friction slowing local modes. The interpretation includes that increasing ion concentration tends to enhance internal friction, evidenced through NSE sensitivity at nanosecond timescales, whereas conformational changes occur due to electrostatic screening, indicated by changes in the polymer swelling exponent. Differences between polymer types and salt values influence hydrodynamic screening radius and interchain coupling, consistent with complementary DLS data. Overall, this figure provides a refined view of polyelectrolyte chain dynamics bridging collective and segmental regimes characterized via advanced neutron scattering and modeled via the ZIM framework with internal friction corrections. Figure 4 compares effective diffusion coefficients DF derived from NSE data for PSS 39K at 30 mg per ml polymer concentration and different salt concentrations. The data points represent experimental DF extracted by fitting the intermediate scattering function with an exponential decay over wave vector Q. Several model predictions are overlaid. The full ZIM internal friction ZIF model with complete hydrodynamic interaction and structure factor correction HQ-SQ shown as a black line. The ZIF model including only the self-part correction DSD0 as a green dashed line, and the pure ZIM model without internal friction tau int equals 0 as a dotted line. Also shown are the ZIF model without correction, green solid, and external diffusion data from DLS and PFG NMR. A key observation is that at low Q and low salt concentrations, the full HQ-SQ correction produces a significant upturn in DF relative to self-diffusion DS, indicating collective effects and stronger hydrodynamic interactions. As salt concentration increases, these differences diminish, consistent with reduced structure factor strength from screening. Above Q, around 0.5 nanometers per mil, quasi-constant HQ-SQ values indicate dominant self-diffusion behavior. At higher Q, deviations from ZIM scaling appear due to internal friction which slows local chain modes, lowering DF compared to pure ZIM predictions. The self-part corrected model aligns well with PFG NMR measured DS, underscoring the importance of including hydrodynamic self-interactions and internal friction. Furthermore, the hydrodynamic interaction screening radius, RHI, inferred from FITS, varies with salt concentration, being lowest at intermediate salt but larger at very low and very high salt. This behavior matches changes in polymer charge and counter-ion absorption, impacting interchain coupling. Overall, Figure 4 quantifies the nuanced interplay of hydrodynamic interactions, electrostatic screening, and internal friction that dictate polymer diffusion dynamics across length scales. Figure 5 presents viscosity-scaled effective diffusion coefficients DEF, measured by NSE for PSS 39K at different temperatures, with data color-coded accordingly. The values have been normalized to the viscosity at 20 degrees Celsius to isolate intrinsic polymer dynamic effects. Experimental points are shown along with model fits from the ZIM internal friction (ZIF) framework, including hydrodynamic and structure factor corrections. Also included is the pure ZIM model without internal friction for comparison. The results show that at low Q, representing larger length scales, diffusion coefficients scale almost perfectly with solvent viscosity across the temperature range, indicating dominance of hydrodynamic friction. However, internal friction parameters decrease as temperature increases, reflecting thermally activated processes such as bond rotation and steric hindrance that impede segmental motion. The authors interpret this as internal friction being sensitive to temperature, unlike solvent viscosity-related dynamics. The inset and supporting information display Arrhenius behavior of internal friction times, characteristic of activated molecular motions. Overall, this figure confirms the distinct temperature dependencies of hydrodynamic and internal friction contributions to polyelectrolyte dynamics, highlighting the need to consider both for accurate modeling and understanding of polymer solution behavior under varying conditions. In summary, this work provides a comprehensive experimental and theoretical analysis of polyelectrolyte chain dynamics in aqueous solution across a range of salt concentrations and polymer charge states. By combining dynamic light scattering, pulsed field gradient NMR, small-angle X-ray scattering, and neutron spin echo measurements, the authors map out both collective and individual chain diffusion behavior alongside structural correlations. Interpreting these data through an extended ZIM polymer model incorporating internal friction and hydrodynamic interaction screening, they demonstrate that charged polyelectrolyte dynamics can be effectively described by decoupling local segmental motions from interchain hydrodynamic and electrostatic interactions. Key findings include the pronounced enhancement of collective diffusion at low salt due to long-range interactions, the modulation of internal friction by ion concentration and counter-ion adsorption, and the temperature dependence of these frictional effects, distinct from solvent hydrodynamics. The 2 Yukawa potential model applied to SAXS data reveals a balance of electrostatic repulsion and short-range attractions, shaping polymer conformation and solution structure. Overall, the study advances understanding of the subtle interplay between hydrodynamics, electrostatics, and internal friction, controlling polyelectrolyte behavior on multiple length and time scales. This insight is critical for designing and optimizing polyelectrolyte-based materials and processes in diverse scientific and technological fields.